Okay, so this is part 2. Like I said, it won't be that long. This is section 4.6, which is fairly short, and it kind of just adds on to what we've been talking about in the last section. Okay, so the row space. Okay, so now, I mean, for the most part, when we talk about the null of A and the column of A, we're looking at the columns, right? We're row reducing and everything, and looking at the columns. Now we're going to look at the row. So the row space of a matrix A, and A is an m by n matrix, is a set of all the linear combinations of the rows of A. Okay, and so just keep in mind here that for a row of A, it's a subspace of Rn, because for an m by n matrix A, each row has n entries, right? And so that's why it's a subspace of Rn. So I just wanted to give you a brief example. So if A is this 3 by 2 matrix, then we can take the transpose, right? So, because this is the set, so the row space, again, the row space of a matrix A is a set of all linear combination of the rows of A. So if we take A and transpose it, then those rows now become columns, and it's another way to look at it, and it's what we're used to. Okay, and so we can now so we just took our rows and took the transpose, so now they're column vectors, and the definition of row space is that it's a set of all linear combinations of the rows of A. Okay, so another way to think about that then is the row of A is equal to the column of A transpose, okay? Because since you're used to working with just the columns and not necessarily the rows, it might be easier to think about it that way. Okay, so we have a nice property with row equivalent matrices. They have the same row space, which is nice. So the theorem says if A is equivalent to B, then the row of A equals the row of B. And if B is in row echelon form, so REF, the non-zero rows of B form a basis for A and B. Okay, so if we wanted to find a basis for the row of A, A is equal to the matrix from the last example, and I row reduced it down here, so you might want to stop and double check. And so they have a pivot. Okay, so by this theorem then, it says that the non-zero rows of B, and so because we row reduce, this is our new matrix B, and the non-zero rows of B form a basis. So here that means, so the basis for row 1 are the vectors 1, 1. So all I did was take that row and create, so it's the vector 1, 1. Okay, so those represent the same, because again, we're looking at the linear combination of the rows. So a basis for row 1 is 1, 1, and 0, negative 1. Okay. If we want to look at the column, so we also could get information about the column in the null space, right? Because remember, the column space, the column of A is the pivot columns, and the null space of A is the non-pivot columns, right? And so if we look at this, because we took our matrix and row reduced it, we have the 2 pivot columns. So then our column of A is the span of those 2 vectors. And the null of A, so we really haven't talked about that. And then the dimension of the column of A is 2. The null of A, we really haven't talked much about, well, what if there are no free variables? Well, that means that the null space of A is just the 0 vector, right? Because again, remember, the null space is the linear combination. You take your matrix and you row reduce it, right? It's the homogeneous solution. You row reduce it down, and then you look to see it at your free variables. But we don't have any free variables. But the 0 vector is always in our null space, right? There's always an element in our null space, the 0 vector, right? Because no matter what linear combination we have, if we make all the scalars 0, we get the 0 vector, okay? And so the dimension of that is 0. And as you remember from the last set of notes, the dimension of the column space plus the dimension of the null space equals the number of columns, right? And so it equals out. All right, so now the rank, which we talked about in the last slide. So the rank again of A is the dimension of the column space of A. And so notation is rank of A, and that equals the dimension of the column space of A. And in that last example, the rank of A was 2. Okay. All right. So now find a basis for row A and column A. Find the rank of A. Okay, so we need to find 3 things. Well, we have this matrix here. So this is our matrix. And so the column vectors, in case you can't see that, the first column is 1, 1, 1, 1. The second column, 2, 3, 1, 2. The third, 2, 1, 3, 2. And then negative 1, negative 2, 0, 1. And so what we do is, so find a basis for the row of A and the column of A. So we row reduce in REF, not RREF. And again, so the non-zero rows become the basis. So we have the basis here, because those are our 2 non-zero rows. And then the column of A, we have 2 pivots there, right? And so then the basis for the column of A would be corresponding to the first 2 vectors in our original matrix. And so that's our basis for the column of A. And as for the rank, and again, the rank is the dimension of the column, right? And so then the rank of A is also equal to 2. So once you have the basis for your column space, you have your rank as well. Here's a warning. Although the first 2 rows of B are linearly independent, so that's these first 2 rows here, they're linearly independent. We can't conclude that the first rows of A will also be linearly independent, okay? And I also want to say, so we can't conclude that that means these 2 rows will be linearly independent. And I also want to make note of my note above here that many rows of B form a basis for row A, right? Because when we row reduce, when we put in REF, that's not unique. So you can have something different. If you stopped and paused the video and row reduced it differently, maybe, then you could have a different basis. All right, so that's not unique when we talk about row of A. Okay, and we're almost done. The rank theorem, and that is given, so given an n by n matrix A, the dimension of the column space of A is the same thing as the dimension of the row space of A. And that is the same thing as the rank of A. So whenever you hear column of A, the dimension of column of A, the dimension of row of A, and the rank of A, that means the same thing. It's talking about the same number. And we're talking about numbers when we talk about dimensions. So be careful not to confuse column of A with the dimension of the column of A, right? The column of A is going to be a span of vectors, but the dimension is going to be a finite number. So that's sort of like vector scalars, right? So just be careful. The rank of A plus the dimension of the nullity of A, null of A, and it's also called the nullity. So nullity is another word for the dimension of the null space of A, and that equals the number of columns of A. Okay, we talked about that already. All right, so last example. Yes, you guys made it through both videos. Good. A is a 7 by 9 matrix, so 7 by 9, so that means 9 columns, with dimension of A, the dimension of the null space of A equaling 2. Find the rank of A. Well, we know the rank of A, which is the dimension of our column space, plus the nullity of A, which is the dimension of our null space, equals the number of columns of A. So we know what the number of columns are, we know what and we're given the dimension of the null space A, the null of A. So we can substitute those values in and solve. And so our rank of A is 7, which is interesting. Look at that. Those are the same numbers. Is that a coincidence or not? Interesting. All right, and then can a 6 by 9 matrix A have dimension of null space A equal 2? Well, I did it again, but it's the same from up above. So again, that means the rank is A. And so no, because the dimension of the row space of A, which again is the same as the rank, which is the same as the dimension of the column space of A, has to be less than or equal to 6, right? Because that's in our row. This is a 6 by 9 matrix, 6 rows. And so 7 is too large, and so no, it cannot. We cannot have a 6 by 9 matrix A that has dimensional space of A equaling 2. All right, we are done. See you in class.